Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is gravitational field intensity, also known as little g, as opposed to the big G that we've been talking about in the force of gravity formula. Today we're going to cover a number of questions that you can see at the top of the screen here, so please, in a moment, pause the video and have a look at what those are. While you're at it, take a look at where we are in the unit schedule. We're still in Lesson 2, and you can see highlighted here the parts that this video deals with. Same thing with the learning goals and success criteria. So please pause the video and have a look at that now. Okay, you're back and we're going to get started. First topic that I'd like to discuss with you is the following. Now, depending on when you're watching this video, we may already have done this in class, or maybe we're going to do it, but we're going to be taking those Newton scales, those spring scales that measure force. We're going to be attaching a bunch of masses to them, and we're going to do a little mini experiment where we attach the following masses, you can see in the data table here. And we're going to measure, when we hang these vertically and allow gravity to pull on these masses, how many newtons of force are registered. You're going to notice when you do this, or maybe you've already noticed because you've already done it, that these are the resulting forces. And so if we plot a graph, then we get a straight line through the origin, which looks roughly like this. You can see that for about a kilogram of mass, the force is about 10 newtons, and it scales linearly all the way back to the origin. Now, if you were in math class, you would be looking at a graph like this, y versus x, going through the origin. And if I asked you what's the equation for that graph, you would say, oh, that's easy. That's y equals mx plus b. Of course, the b value, the y-intercept, appears to be 0 here. So you would just say y equals mx, where m is the slope. Well, in a similar way, that's kind of what we have here. Only we don't have y, we have f, and we don't have x, we have mass. So you could say F equals slope times the mass. And the slope, as I'm sure you can see if you do a rise over run calculation, is approximately equal to 10. In fact, in this example, it's exactly equal to 10. In class, when you do this, and we get a number 10, I like to ask people, well, what number do you know of in gravity that's very close to 10? And usually the students yell out, oh, 9.8, because they're connecting the idea of gravity, 9.8 meters per second squared acceleration, with the 10 here. They're very close. And you would be right. In fact, force does equal 9.8 times the mass. Let's just take a look, however. What would be the units of this? Rise is measured in newtons, and run is measured in kilograms. So rise over run, I'm going to give you newtons per kilogram. And this is, in fact, an equivalent unit to meters per second squared. So you'll be able to see a little bit later in this unit that I'm not pulling your leg here. I'm not selling you a bag of goods. This is actually true. A meter per second squared is a newton per kilogram. But for now, the force of gravity acting on any object is equal to 9.8 times its mass. And since this number is constant on the surface of Earth, we give it its own letter. The little g letter is what we give it. So you'll often hear physics students write F equals mg, like this. And this is an important formula, so I'm going to highlight that just like that. F equals mg. This tells you the force of gravity acting on any object near the Earth's surface, and we have a name for that force. Other than gravity, we also call it the weight of an object. So weight, I know you go to the doctor's office and the guy says, step on the scale, says your weight is so many kilograms, but actually weight is measured in newtons. It's a force. So the next time you're at the doctor's office, you can correct the doctor who's supposed to have studied physics at some point in the past. Say weight is a force. It's measured in newtons. And this is our formula, F equals mg. Don't ever forget that. That's one that you'll probably remember a long time after this course is done. All right, moving on. So let's take a look at another way that we could calculate the force of gravity. If force of gravity is weight, then how else can we do this? Well, try to imagine yourself on the surface of Earth as you are right now. You're probably right around here in Toronto, as you can see on the map. However, to make this a little bit easier, let's put you somewhere out in the Atlantic Ocean here. I apologize if you don't know how to swim, but you're on the surface of the Earth, and the force of gravity is pulling you down toward the center, of course. That's what's holding you down. Now, you know that we learned this formula in a previous video. Big G, mass of any two objects multiplied, divided by the distance between them squared, is equal to the force of gravity. In this case, the big M would signify Earth's mass, because that is one of the objects involved here. Little m would signify u, right here. So there's little m, here's big M. And d squared would be the distance between their centers. So imagine peering into the center of the Earth, and the distance here would be d. Now, of course, that is also equal to the planet radius if you're standing on the surface. So really, we have a formula for calculating the force of gravity on you that doesn't quite look like this formula I just showed you back here. But they should give you the same value. After all, the force of gravity is the force of gravity. So in fact, these two are equal. So even though I wrote versus over here, it's not really a competition. These guys are equal. They should give the same value. Here's what I'd like you to do right now. In a moment, pause the video. Look up the mass of the Earth. Look up your mass, or weigh yourself, or if you want, just use 60 or 70 kilograms. Find out the radius of Earth, and I want you to plug in big G. Remember, that's the 6.67 times 10 to the negative 11 number that we learned a little while back, times the mass of the Earth, which is roughly, well, I guess I'm telling it to you now, so you don't have to look it up, 6 times 10 to the 24 kilograms. Your mass, I don't know, 60, 70 kilograms, let's call it 65 just for fun. Divide that by the radius of Earth. I'm already in this far, I might as well tell you the rest of it. It's 6,380 kilometers. Convert that to meters, don't forget. And also don't forget to square. And tell me what number you get. Now, do the same using this force of gravity formula that we just learned over here in this screen. Multiply 9.8 times your mass. And tell me what you get. Pause the video and do that now. Okay, and you're back. And are you surprised? Whatever number you got down here is the same as what you should have got here. In other words, what we're saying is that this is equal to that. It should not come as a surprise to you. The force of gravity is the force of gravity no matter how we calculate it. So let's take a look at what that does for us. It tells us that big G, mass of the planet that we are standing on, times m, the mass of any object on its surface, divided by the radius of the planet squared, is equal to the mass of any object on the surface times g for that planet, in this case Earth. Now what do you notice? The m's cancel, and that leaves you with a formula for g, which says that g for any planet is big G, so little g for any planet is big G times the mass of the planet divided by the planet radius squared. And that, in fact, can be used for any planet, or for that matter, any celestial object that you care to consider, which is kind of cool, because as you're going to see very shortly, we can use that to calculate the expected value of acceleration due to gravity or gravitational field intensity on a planet, say, like the moon, that maybe we're going to go land on and explore. Let's try using this formula to do some calculations. Here's one. Part A. What is the value of G at an altitude of 500 kilometers, roughly where astronauts live and work on the International Space Station? So 500 kilometers, I guess I'll specify here. It does say altitude, but that means above the surface, and I'm assuming Earth here, because I'm talking about the International Space Station and Earth. So if you go back to this diagram here, where we can see the Earth, what I'm asking you is the following. If you imagine that here is Earth, and we already know what the radius is because I just told it to you down here, right? That's this number here. So here's the radius. But now I ask you to imagine the astronauts who are orbiting Earth at a little bit above the surface. How high above? Well, roughly speaking, a lot of the astronauts are about 500 kilometers above the surface. So you got to add a little bit on to the radius here. Now, the R value that you're going to use is going to be R equals the 6,380 kilometers plus the 500 kilometers. So don't forget that. And also don't forget to convert that into meters. What I'd like you to do is calculate the value of G at this location. We're still above Earth, so you're still going to use the mass of the planet, being 6 times 10 to the 24 kilograms. But calculate G there. Now before you do it, here's what I want you to predict. We've all seen videos of the astronauts tumbling through space and enjoying their weightlessness. What do you think you're going to get for the value of G when you calculate it? Okay, pause the video and do that now. All right, and you're back, and what did you get for G? You probably got a number that's a little bit less than 9.8. However, how much less? Not very much. In fact, I'm going to go do this right now. I'm going to pause my recording and do that for you. Hold on a second. Okay, folks, and I'm back now. I just did this calculation, and the value that I got for g was about 8.5 meters per second squared. Less than 9.8. Why less than 9.8? Well, because we are farther from the center of Earth when we were up in orbit, and distance being in the denominator, having a bigger denominator, makes the value of the overall fraction become smaller. But here's what might be surprising to you. When I asked you to pause the video and predict a value, maybe you predicted less than 9.8, but did you predict 0? Because a lot of people do predict 0 for the value of acceleration due to gravity in orbit on a space station. The reason is they always see those astronauts tumbling around in 0g. And it makes them think that this value will be 0. But the calculation shows us it's not much less than 9.8. Why are those astronauts not experiencing gravity the way we do here on Earth? I'm going to leave this with you to figure out on your own and to do a little bit of research. It's always good to ask questions that kind of leave you puzzled and inspire you to go find out. The question, once again, why do the astronauts who seem to be in 0 gravity, why are they actually in quite strong gravity? In fact, this gravity is so close to Earth's 9.8 that you might not even notice much of a difference if you were experiencing 8.5 on a regular basis. Moving on. Oh, by the way, and we will talk more about this in class, but I do want you to do a little bit of research on your own. Question B. What is the value of g at a location equal to 1 Earth radius above the Earth's surface? So here, once again, we're calculating g somewhere off of the surface of Earth, but this question's framed a little bit differently. It doesn't give actual values for how many kilometers. It just wants you to know that if this is the radius of Earth, as we've been discussing it, then what does it mean to be 1 Earth radius above the surface? Well, it means pretty much exactly what it says. It means this time, imagine going double the distance from the center as you were before. So if the first distance is 1 Earth radius, here's what 2 Earth radii look like. Now you are up here. So now, what are you going to use for r? Well, if you guessed 6380 kilometers plus 6380 kilometers, then you are correct. Of course, don't forget to convert to meters, otherwise you will make a mistake in your calculation. And don't forget to square the radius. A lot of people forget that. Here's a question for you. Do you even need to do a calculation here, or can you predict what the answer will be? See if there's a quick way of predicting the answer. I'll give you a moment to think about that. All right, and you're back. And if you think about it, what we're doing when we ask you to go from this location on the surface, where g is 9.8, up to a higher point that is double the distance away, we know we will get less than 9.8. But can you tell me exactly how much without a calculator? I'll give you a hint. You're doubling the distance. And in the formula for g, there is the distance squared. So I guess in a sort of weird mathematical way, you could say you're doubling squared the denominator. What happens when you double something and square it? It gets 4 times bigger, doesn't it? 4 times bigger in the denominator makes your value of g how many times smaller? If you guessed 4 times smaller, you're right. So that 9.8 will become 9.8 divided by 4, which is around 2.5. And I'll let you go do the actual calculation involving this number of meters, don't forget to square, the mass of Earth, big G, and the actual calculation. Try that and see whether you get the same value. Moving on. Okay, here's a sample problem involving gravitational field intensity, just to make sure we're all on the same page here. They ask you to calculate the mass of an object. So if we write given, required, and an equation, what are those going to be? We are given the downward force of gravity, Fg. We know that we're on Earth, so g is also known to be 9.8. They're asking us for the mass. What equation should we use here? Fg, m, and g. If you guessed this equation that we learned, you are correct. So this is a very simple question for you to try. You're just going to write Fg equals mg. You're going to put in 1200 newtons as the weight equals the mass that we're trying to find times 9.8 newtons per kilogram. And if you look at this, newtons will cancel with newtons. That's going to leave us kilograms, which will end up being divided up to here, and you're going to solve for the mass. And I'm not going to do this for you because it's pretty straightforward. All right, here's a trickier problem involving acceleration. Sorry, I keep saying acceleration due to gravity because they're very similar, but gravitational field intensity. Here's a little brain teaser. I'll give you the answer and we'll take it up in class, but here's the question. The gravitational field intensity on the Earth's moon, surface of the Earth's moon, is 1.6. I've mentioned this in class before, especially when we saw the hammer and the feather video a little while back when we did acceleration due to gravity. However, if you don't recall, well, I'm telling you now, it's just 1.6 newtons per kilogram. So on that airless surface of the moon, yes, there's still gravity. The astronauts are a certain distance from the center of a planet that we call the moon. They've got little m, the moon has big M, maybe call it M planet, and it has a radius. 1.6 is what they get for g, much less than on Earth, and that's why things seem to fall so much slower than on Earth. What would be the value of g on the surface of another planet's moon if that moon was 1.5 times more massive? So now we're taking this mass and we're going to multiply it by 1.5. We're going to imagine a moon that is heavier, 50% heavier. And we're also going to imagine that the radius is only 75%, so 0.75 times the radius of the planet. So it's a more compact, yet somehow heavier, in other words, it's a more dense planet. So this is the new radius of planet. This is its new, I'll draw it bigger, mass of the planet. What would you get for g? We know that g, little g, is equal to big G, mass of a planet, over the distance, the radius of the planet, squared. So here's the question. If you know that the moon with a certain mass and a certain radius gives you a value of 1.6 when you plug in the actual numbers into this equation, what would you get on the other moon? And I'll give you a hint to get you started. This other moon that we're going to imagine being 1.5 times more massive, you're going to have to multiply the numerator times 1.5, which is going to increase the value of that moon's g. However, at the same time, I'm asking you to imagine that that moon is smaller, so the people standing on the surface are closer to the center. That will make the denominator smaller, and that will correspondingly make the g value even larger. Never mind the fact that it's a heavier planet. You've also got a smaller lunar or a smaller moon radius there. And don't forget to square it, so it's even worse. This will further serve to increase the value of this new moon's g value. You're going to get a lot more than 1.6. I'm giving you the answer here. It's 4.3. But can you do this mathematically? That's what I want you to try on your own. We're going to take this one up in class too, so be prepared. Drawing on our discussion still of gravitational field intensity on other planets, here's a table taken out of your textbook, Physics 11 by Addison Wesley, gravitational field intensities of other objects in the solar system. This is more for fun for you to look at, but look at all these different objects, planets and the sun and our moon. Their masses given, their radii given, and look at the huge range of values for g on various different objects. The moon having the lowest of these objects, the sun having the heaviest. The sun is very, very massive, much more massive than, say, Earth. In fact, if you look at it, it's about 300,000 times more massive. In the mass department, that much bigger. So why is its g value not 300,000 times more massive? Well, there's another factor, of course. There's the size factor. On Earth, you're much closer to the center of the planet when you stand on the surface. On the Sun, you are much farther. In fact, you are about 110 times farther than on Earth. So the added mass serves to increase g. The added distance from the center serves to decrease g. Which factor wins? Well, in the formula that looks like this, the factor that wins, well, does 330,000 times more up here counteract 110 squared times more down here? Looks like it does, because g on the Sun is greater than on Earth. This would crush you. And that, by the way, is the fact of the video. The g value on the surface of the Sun, 270 newtons per kilogram. And hold on one sec, I'm just going to pause the video to get my class in here. Okay, folks, just to finish off, let's see where we're at here. Oh, we're done. Isn't that funny? Always a nice surprise when things turn out for the best. Anyway, hope you enjoyed the presentation. I know I went a little bit fast today. There were a lot of things to cover, but just to recap, we were talking about a new way of calculating the force of gravity, also known as weight, using mg. This leads to the idea of gravitational field intensity. And we did a number of calculations in order to do that at given values of distance from the center of a planet. And we also talked in terms of what are called proportionalities, where we didn't give exact values of mass and distance, we just talked in terms of ratios. Make sure you're able to solve both kinds of problems. And we finished off with a comparison of g values on various different objects, and we talked about how it's not just how heavy you are, it's also how far away you are from the center. All right, folks, have a great day, and I will see you in class. Thanks for watching.